Okay, this time we'll be looking at the expected value of a continuous random variable. So remember, the expected value of a random variable is a sort of long-term average you'd get if you kept asking that random variable to give you numbers over and over again. So going back to the bird on the wire, it would sort of be like a long-run average landing position of the bird. Okay, so it'd be very helpful to be familiar with the discrete version of this, so do look back on that if you need to, because we'll be borrowing a lot of those ideas to make sense of things later on. Okay, so we'll again start by taking the simplest case of a uniform distribution. So we're going to have the bird land anywhere at random on the wire with no preference for any particular section. And this time we'll actually label the wire with some numbers, and I'll just say from 0 to 6 or something. Okay, and we'll attach a y-axis to this before drawing our probability density function, which for the uniform distribution is just this straight line here. Now, we don't exactly need to calculate this right now, but just so we're on the same page, we'll work out how high this function goes on the y-axis, right? Remember, we insist on the total probability being 1, which means the total area under the line here must equal 1. So since its width along the bottom is 6, the height must then be 1 over 6, so you'll see it's at something like 0.1666 repeater or something. Okay, now it's worth making sure we're okay with that calculation, but honestly we don't really need to know that because for this function, if the bird lands anywhere on the line without any preference whatsoever, I hope we should just be able to agree that the average must be right in the middle here. So in this case, it would be at x equals 3, right? I hope that's sort of obvious and agreeable, so we'll use that as our starting point. Okay, and as before, we'll now turn this into a case where the bird favors one particular section of the wire, and so we change the density function to this guy here. So obviously the bird prefers the right side, in particular the section from x equals 4 to x equals 6. But what exactly do we mean by that? Well, remember, the probability of the bird landing in any section of the wire is given by the area under the yellow line in that section. So let's start with this blue section here. Okay, the probability of the bird landing between x equals 0 and x equals 4 must be the area of this shaded rectangle. Now the width is, of course, 4, and the height is 0.1, that's the yellow height there. So we do 4 times 0.1 for the area, and we get 0.4. Likewise with this section, the probability of the bird landing between x equals 4 and x equals 6 must be the area of that shaded rectangle. Okay, the width is 2 this time, that's just the gap from 4 to 6, and the height of the yellow line there is 0.3. So we do 2 times 0.3 and we get 0.6. Now, of course, we could have just seen that if it's got a 40%, so 0.4 chance of landing in the blue section, well, it must have a 60% chance of landing in the green one, okay? But I guess what we've just checked is that our yellow function does indeed give a valid legal probability distribution because everything neatly adds up to 1. Okay, so what this means is that 40% of the time, the bird lands somewhere in this interval from x equals 0 to x equals 4, and it does that with no further preference. Likewise, 60% of the time, the bird lands somewhere in this interval from x equals 4 to x equals 6, and it does that with no further preference. So then it makes sense to sort of treat this whole distribution then as two separate cases of the uniform distribution. It's like two uniforms sort of glued together. And what I mean is this: if we just look at the blue section, okay, if the bird lands in here, it's pretty much just a uniform distribution between 0 and 4. And we agreed that the average here would be right in the middle, which is at x equals 2. Okay, that means when we're thinking averages, we'd pretty much be landing on average on this number 2 40% of the time. Now, in the back of our minds, we know it's not actually 2, it's actually somewhere uniformly distributed between 0 and 4, but just for the purpose of getting the average, it may as well just be 2. Okay, similarly, if we now look at the green section, if the bird lands in here, it's just a uniform distribution between 4 and 6, which we know should have an average of 5. So again, we know in this case that 60% of the time the bird is landing somewhere between 4 and 6, but for all practical averagey purposes, that may as well be landing on the number 5, 60% of the time. And so what we've done is we've pretty much condensed this continuous distribution into something that looks like a discrete random variable. It's like you hit the number 2 40% of the time, and you hit the number 5 60% of the time. And again, we need to pause here and say that the distribution itself is entirely different to this discrete sort of thing we've just come up with. Okay, it's only because right now we're only looking at averages, expected values, that we're able to kind of turn it discrete just to make sense of the calculation. And the calculation itself for the expected value is now identical to the discrete one, where you multiply each outcome by its probability like this, and we get 3.8 here, which, as expected, is sort of just slightly higher than the average for the uniform distribution, since here the bird preferred the section on the right side of the wire. Alright, so let's recap what we just did. Okay, our distribution gave us sort of 2 rectangular areas, which we considered as sort of 2 separate uniform distributions. Each of these areas had some sort of contribution to make to the total expected value, right? And the contribution it made was equal to the sort of probability spanned out by that section multiplied by the average value of that section. Okay, and that's a contribution that each rectangle made to the final expected value. Okay, so how does this idea help us calculate the expected value for a general probability density function, say this curve here? Okay, well, we just worked out what to do when our density function gave us 2 rectangles to deal with. Okay, and from calculus, setting up an area under a curve is really just chopping it up into, well, not 2, but heaps and heaps and heaps of really thin rectangles, right, whose widths limit to 0, and to integrate was just to add up all these rectangles together. So really, with any density function like this, we're actually still dealing with a bunch of rectangles, just really thin, tiny ones, and we expect in the end to have to integrate to add them up. Okay, but let's make these rectangles a little bit thicker now so it's easier to see. But remember, in the back of your mind, by the time we integrate, we're going to limit their width all the way to 0. Okay, so we'll focus on one particular rectangle centered at some, say, x value here, okay, which we're going to call it x. Okay, the height of the density function at this x value we'll call f of x as normal, so f is the probability density function. Okay, so what would be the contribution of just this tiny little rectangle to the total expected value? Well, we had to work out the probability of landing in here first, which would be the area of this really thin rectangle. Okay, and we know the height is just f of x, but for the width, we need to look a lot closer, and we see the width is this tiny little guy, which traditionally we call dx, okay, which as usual means we're going to eventually limit this width to 0. Now, while we're here in this view, remember we're also interested in the average sort of x value across this interval, and we're going to go ahead and just say that the average value is x itself, right, the number on the x-axis we built the rectangle from. And I know you might be a bit nervous about all these other x values the purple arrow is traveling along, but remember, dx is shrinking to 0. So in fact, in the limiting case, the purple arrow effectively doesn't get to move, or not any significant amount anyway, and we can confidently say the average over that tiny vanishing interval is exactly the x value itself. Okay, so coming back out, what is the contribution of this little rectangle to the total expected value? Well, we land here with probability f of x dx, the area of the rectangle, so the height times the width, and the average value of this tiny little interval is just the x value itself, so we multiply that by x. Then we want to add up all the contributions of each of these rectangles, so all of these guys here, and then we limit the width of these rectangles to 0, and by the time we've done that, our calculation is fully exact, and that's done by integrating our expression. Okay, again, I'm writing from negative infinity to infinity, but what I mean by that is just over all sensible possible values of x you can come up with. Okay, so for this particular curve, we'd just be integrating from 0 to 6. Okay, but given any probability density function, we can now work out its average by multiplying that function by x itself and integrating that expression over all possible values of x that your function is defined over. Okay? Alright, just before we finish, I hope you can see how even though discrete and continuous probability distributions behave really differently and are handled quite differently, there's quite a nice link between them that we get when we think carefully about what exactly integration is. And that's sort of why the expected value formulas, if you will, for discrete and continuous random variables look so much alike, right? Because here's a discrete one on the left, remember that from the past, okay? And the continuous one we just came up with is literally the same thing, except that the sum has been changed into an integral. And while that gives you a convenient way to remember these calculations, and it's a sort of recurring theme over probability stuff, right? To go from discrete to continuous, you just change all your sums to integrals, right? It kind of works most of the time, if not all the time. Okay, but put that aside for now. I hope you've seen there's something really beautiful going on behind that, and that really comes from the brilliance of calculus. Here in particular, the remarkable idea of integration, which is to add up a bunch of rectangles, which itself is an entirely discrete problem, right? You have a bunch of rectangles, you add up each one separately. That's a discrete thing, right? But then just by limiting the width of these rectangles to 0, we've suddenly stumbled upon this bridge into the world of the continuous, and I think that's really nice. Okay, and this idea does go much further, all the way to the foundations of what integration is, what measure is, what's area, what's volume, what's measure, and actually this gives us a way to unify discrete and continuous types of variables. Okay, but that would take us into a whole new world called measure theory, which is way beyond the scope of our course, but that would be something to look into later if you're interested. Okay, but that's all for now, so see you around.